All right, thank you to everyone who's already here. We're going to go ahead and get started with our Q&A app building webinar featuring our new integration with Haystack. We will be posting, or rather sending everybody that registered the slide deck, this recording, and the code demos, notebook, etc. From today's webinar. So if you'd have to leave early, if you would like to share with your colleagues, whatever the case may be, you are welcome to do so. The follow-up email to this will come out tomorrow. Brandon is currently sharing his screen, which is great. As mentioned, this is a question and answer application webinar featuring Pinecone and Haystack's new integration, which Brandon Chan, the machine learning engineer at DeepSet, and James Briggs, our senior developer advocate here at Pinecone, will detail further. If you have questions that arise throughout the webinar, please put those in the question and answer field that you should see at the bottom of your screen. That way our presenters will be able to answer your questions in a more streamlined fashion throughout the webinar. And we will place those questions as well on our community page so that the answers can be recorded somewhere too. And with that, I'm going to pass the baton over to Brandon to begin.
Okay, can you hear me now?
Yep, all clear.
Great. Yes. So yeah, thanks very much, Sophie, for having me here, and thanks for everyone from Pinecone and all the everyone who's attending today. Very happy to talk today about question answering and the question answering applications that you could be building with Haystack and Pinecone. Just to give a bit of an overview of what we're going to cover today, I'm going to start off by talking a bit about what question answering as a task is, how you can use it, what use cases there are, and how Haystack is going to enable you to build cutting edge end-to-end systems that perform question answering. I'm going to pass it over to James after that to talk a little bit more specifically about this Haystack and Pinecone integration. And then we're going to move on to a demo at the end where we'll see what a completed running Haystack application looks like, and then also go through a notebook which shows you all the components in Python code that you need to create such a system that has both Haystack and Pinecone. So I would like to start off by talking about the task of question answering. Question answering is more specifically an NLP task that goes something like this. Maybe you start off with a question like, what is Berlin? And perhaps you have a document. And in this case, as an example, we might have, say, the page from Wikipedia about Berlin. And a well-trained question answering system should be able to highlight for you the section of text in this document that answers the question. And in this case, the answer would be the largest city of Germany. And the latest approach to this is using something known as a reader model, which actually tries to identify the start and end of answer spans. And it is essentially a language model that is trained on question and answer pairs. When I talk about these models, what we're actually talking about are machine learning models that are based on this transformer architecture that has become very, very popular and very, very successful in a lot of different tasks. The SQUAD dataset is the default dataset for this task. SQUAD stands for the Stanford Question Answering Dataset. And you might be asking, why is it now that you're hearing about question answering? Well, transformers, these models that I just talked about, have really kind of bumped up the performance of question answering systems very recently. This has brought with it a really big momentum in research. And the systems that we build out of this turn out to be actually very applicable to real business problems. So we kind of see this interest from both an academic angle, but also from the business side of things. Some use cases that we've been seeing using Haystack, and not all of these are directly question answering, but using Haystack and using NLP and the power of transformers, we've actually seen quite a lot of use cases pop up where frameworks like Haystack and Pinecone will really, really assist you. So what I've been talking about just now is question answering search. The idea is that you might want to ask a question into a textual knowledge base. You might want to return sections of text as answers, and this is actually really good for companies that perhaps have documentation internally, or just any kind of unorganized collection of text. These NLP systems are actually also very good at handling semantic document search and FAQ search. You can find out more about those on if you want to dig a little bit more into Haystack and have a look at our website. But today I'm going to be focusing in on question answering search. So those of you who were paying attention to that first slide might have picked up on the fact that I mentioned that question answering in that case operates on a single document. And while that is a really cool result to have if you can actually get this answer out of the document, this doesn't really reflect the kind of search that you might want in a real enterprise setting, because you're much more likely to have a large collection of documents rather than a single document. And so with that in mind, I want to talk about a different task here, document retrieval. And I hope that you can see how this is going to dovetail in with question answering in a minute. So document retrieval goes like this. You start off with a question or a query. It might be something like, what kind of dog breeds are there? And then you pass on this to a retriever whose job it is to return a set of documents which it thinks is relevant to your question. It doesn't actually have to do the exact highlighting, just returns a whole document here. And there are some approaches known as the keyword-based approaches, which I think many of you might have heard about before. They include TF-IDF and BM25. These are very fast and lightweight and effective approaches, but they're also known as bag of words approaches, which means that the word order actually doesn't really matter to them so much. As long as a word appears or it doesn't appear, that's what it draws its intuition off of. You'll see that this contrasts against the transformer-based approaches, also known as dense retrieval approaches. So these include things like DPR, which stands for dense passage retrieval, but also sentence transformers. And these, by contrast, are actually very syntax sensitive. It actually really matters what order these words come up in and what the structure of a sentence is. Because of this, there's also a lot more computational power needed to index and to query, because there's a need to turn text into vectors and then also to do various comparisons between vectors. And because of this, dense retrievers benefit hugely from having some kind of vector optimized storage option. And this is exactly where Pinecone comes in, where this integration with Pinecone offers a really easy way to start using a remotely hosted vector optimized database. So having both question answering and document retrieval is how we're actually going to perform question answering at scale. And the pipeline looks something like what you see on the left there. So if you start off with your collection of documents, you want to first use your retriever to collect a set of candidate documents, which you then pass on to the reader, which does the finer reading of these documents to finally highlight an answer that is relevant to your question. The reason why we have this kind of a setup is because the reader is in some ways challenged by certain facets of this task. So readers, for example, are limited in the length of input that they can take. And also readers take up a lot of computational power at query time, which means that the reader has a big impact on the speed. It really actually takes up most of the computational requirement at query time. And also, if you're performing this question answering on multiple documents, your reader might be returning answers, like multiple answers. And then there's an extra step that's needed here to say, how do we pick the right answer out of this collection of answers that's being returned? And so a lot of these problems can be handled by the combination of having a retriever and a reader. because this is a very efficient way to look at large collections of text and perform question answering. The retriever essentially acts as a lightweight filter. It's like a first stage of filtering, which then only passes on a subset of the documents to the reader, reducing the amount of computation that needs to be done by the reader. And to give you a sense of how much improvement we can get here, we were running an experiment using the natural questions development set. There's about 7,500 documents, and we were using a Roberta base model and also a Tesla V100 for GPU acceleration. And if we were using just the reader by itself, we were seeing that queries were something in the range of about 3 hours, more than 3 hours actually. But once we put in a retriever beforehand, we could get this down to having a query every 0.5 to 2 seconds for very minimal performance drop. So I already mentioned Haystack, and Haystack, it's worth really explaining what is possible with Haystack here, because Haystack is a fully open source NLP framework. Today, we're just going to be focusing on question answering, but there's actually a lot more than question answering that is possible with Haystack. But nonetheless, all the core NLP tasks are covered in Haystack, and Haystack is production focused as well, which means that this isn't just about playing around with some models in a Python script. We offer everything that's needed in order to actually run this as an application that can communicate with other applications. And also we offer a lot that allows it to scale so that you're actually working the kind of scale that is useful in a real world application. I want to mention here also that we have an integration with the Hugging Face Model Hub. Some of you might be familiar with this model hub. This is where a lot of transformer models are kept, and our integration makes it super easy to download the latest models. All you have to do actually is to change a single name string, and you can automatically download and start using a model that was uploaded. And Haystack is end-to-end. It's really not just the models. You shouldn't think of it as just being sort of individual components. We've put a lot of time and effort into building out the connectors between components. So for one, of course, we have this integration with Pinecone, which we're really, really glad to have. But yeah, there are like lots of quality of life features for all users. And we're thinking about really the whole process of working with NLP models and creating pipelines, not just kind of the one modeling part. We're really thinking about an integrated set of tools. Just another look at what there is in Haystack. As I said, all the core NLP tasks are covered. And up there, we see a list of different nodes that are available. So I've already talked a little bit about the reader and the retriever, but we also have a question generator, which can generate a list of questions out of a document. We have a summarizer node. We have a ranker node. We have a generator, which is a kind of replacement for the reader. It operates in a very different way to the reader, but ultimately performs the same task. And then we also have a classifier so that you can apply a classification model to your documents and attach that to your documents as metadata. And also a query classifier to say whether your incoming query is in the full sentence question style, or if it's just a collection of keywords. We have a lot of connectors as well, so that you can start using TXT files, PDF files, docx files, markdown files. Those can all be converted to something that will gel with Haystack. And we also provide a preprocessor to split long documents into clean text. And we supply also everything you need to get started with a REST API, and also we also have a demo UI that you'll be seeing a little bit later on, which will make it really, really easy to create your first application for question answering. That is something that you can actually show to someone and let them use, even if they have no programming experience. And some of the workflows that we support are obviously indexing and querying with filters. That's really the bread and butter. But we've also seen that there are a lot of companies and also research teams who want to perform evaluation. They want to know exactly how good their model is after they've trained it, and also know how good it is for a certain set of data. Within Haystack, there's also the possibility to retrain reader models and also DPR, dense passage retrieval models. And we also provide various tools so that you can perform annotation more efficiently. And with that, I would like to pass it over to James.
Thanks, Brendan. Yeah, so we're just going to go through a little bit of the vector databases and how they fit into this whole question answering pipeline. So let's go on to the next slide. So just to explain what a vector database actually is first. So when you are storing all of this text data from your documents that you want to be able to search through using sort of natural language questions, you're going to use a transform model, as Brandon mentioned before, and create these dense vectors. Now, these dense vectors are incredibly useful because they store a lot of information. So we are almost kind of like numerically representing the meaning of whatever is behind those sentences and paragraphs, which is really cool because when you then place these vectors into a vector space, you will see that similar sentences or the meaning behind sentences that is similar, you will see that those vectors end up in a very similar vector space. And you can almost represent different pieces of semantic information based on where vectors are in this vector space. So, well, one, it's super interesting, and two, we can take advantage of that because then we can compare these vectors. So if we ask a question and we feed that into a dense retrieval model that has been trained to place questions and contexts or paragraphs or like the answers to those questions within a similar vector space, you can then begin asking a question in natural language, like you would ask a normal person. And you can then, in your vector database, return the most likely answers to that question. And that, I think, is really cool. And that's the vector database part of it, the actual storage of those vectors and the calculating the similarity between vectors and returning particular vectors. Next slide. So Pinecone is, of course, a vector database. It's fully managed, and we'll go a little more into that in a moment. But in essence, it's going to make tasks like semantic search and open domain question answering super easy. And in particular, the storage of vectors and querying those vectors is what Pinecone makes super easy. But there are, of course, other components, particularly with open domain question answering, that we don't deal with and Haystack deals with. And we'll jump into that in just a moment. But those two things together really does make things like Q&A incredibly easy. So yeah, that's where we make vector search easy, but the remaining steps of, for example, open domain question answering are still up to the user. And that's really where the Haystack integration idea came from. So if we go to the next slide. So at a glance, this is a very simple pipeline for open domain question answering. So you start in the top left with your data source. That can be things like PDF documents, web pages, any sort of text data. You need to pre-process that in some way, and you get your process context, we call them, which is basically paragraphs, and we pass them to a retrieval model. That creates the context vectors that get stored in Pinecone, and then there's all this, there's all these different components that all go together. And like I said, this is a simple, very high-level overview of the whole pipeline. In reality, it can get much more complex. Now, yes, with Pinecone, you get the vector search part of it is super easy. But we were finding in the past that, okay, the vector search part is easy, but then the rest of it is super complicated, and you need to understand how each component fits together and so on. So that's where, of course, Haystack comes in. So if we go to the next slide. So with Haystack, you basically just abstract all of that away. So you don't need to worry so much about how is your retriever and reader going to fit together? How is it going to communicate with Pinecone? How are you going to deal with the pre-processing? All you really need to do is say, within Haystack, I want to use this component, this component, this component, and Haystack really, puts all those together and makes everything so incredibly easy. So by putting both Pinecone and Haystack together, we get like an incredibly powerful and incredibly easy to use open domain question answering pipeline. So when you're putting all this together, you only really need to think about how does a user query go into your pipeline, how does your data source go into your pipeline, and how do you want to show the answer at the end of that. It's super easy. So next slide, yeah. So at least the reasons for us as to why the Pinecone document store is particularly useful. The first one is it's incredibly simple to use. So this code on the right you see here, that's if you're using Pinecone directly, but if you're using Haystack or using Pinecone document store inside Haystack, it's even simpler. You don't even need to worry about any of that. Haystack handles it for you. So all you actually need to do is you create an account on Pinecone and you initialize your document store in Haystack and you pass an API key, and that's literally all you actually need. And another thing is that Pinecone is managed. So rather than when you're putting all this together, you don't need to worry about the infrastructure for your vector database. You don't need to worry about the security or the performance, because putting a vector database together is an incredibly hard task. So using Pinecone abstracts all of that away, so it means that you, as a developer, can actually focus on whatever it is you're building rather than all of these other things that contribute to what you're building, which is, I think, an incredibly useful feature. Next slide. So another reason as to why I think Pinecone is a great document store is that you get a almost instant refresh, and for most purposes it is basically instant refresh. You can, in like a Python script, you can upload your vectors, and on the very next line you can query and actually return those vectors immediately, which is incredibly fast and super cool to actually see that when you're using it. And the same applies for deleting vectors and so on as well. So another key reason is Pinecone is very scalable. So you can scale to billions of vectors and it will just work. So you don't, in most cases, it's very hard to get past even like a million vectors. It can be difficult to do that with good latency speeds. With Pinecone, you're going to get good latency at billions of vectors, which is very hard to actually do. Next slide. So another thing that we're super proud of at Pinecone is single stage filtering. So single stage filtering is essentially a incredibly efficient and fast form of filtering. So in your, you have your natural language question, but maybe you want to be more specific. Maybe you want to restrict that question to a particular set of documents, or maybe you have a particular date range or something along these lines. So alongside your query, you can include a filter. And that is a really cool feature of Pinecone, and it's reflected in Haystack as well. Haystack has their own or introduced filtering, and we can use that filtering in our Pinecone document store and make use of Pinecone's incredible filtering capabilities, which is really cool. Next slide. Okay, so I'm actually going to hand over to Brandon here. He's going to go through a really cool demo. So I'll let you go ahead with that.
Great, thanks. Yes, so I would actually quite like to start off by showing what a Haystack application looks like. And here we have a publicly available demo, actually. It's at haystack-demo.deepset.ai. And in this case, we have a Haystack question answering system running. And we've indexed some documents from Wikipedia about countries and capital cities. And so if I ask the question, what's the capital of France? This model will run. And oh, no, that's okay. Sorry, it's changed to which countries border with Mongolia. And as you can see here, we get quite a bit of information here. We've got, we see that the source is this page, the Wikipedia page about Mongolia. And if we want to see whether this answer here, Russia to the north and China to the south, is correct, we might want to read a little bit of context around it. So it says, it is bordered by Russia to the north and China to the south, or its neighbors in a Mongolian, and here with, so as you can see, this model is actually capable of understanding questions like this and returning these answers. We can try a couple more. Let's try, who's the current king of Spain? Here we have it. So an article about Spain. Commander-in-chief is the King of Spain, Felipe VI. Nice, nice. And one more that I want to ask here. What is the largest city in China by population? And you can see here that it's highlighted Shanghai. And maybe once again, we want to read around the answer a little bit, read the context a bit to see if this is really the answer that we want. This is actually a really nice step in sort of validating these answers because, people want to be able to check whether this is the right answer or why this is the answer. Being able to read the text around it is a really, really useful tool for that. So if we read this, it says a megacity, Beijing, is the second largest Chinese city by urban population after Shanghai. And so we can see that it's correct here, but also that it's not just operating on some sort of set of rules or templates. This model has actually had to read the query, read the sentence, and understand how the sentence is constructed. It's sensitive to the word order so that it knows that the answer here is Shanghai and not Beijing. So you might be wondering, how do I build a system like this? And for that, we're going to show you this notebook over here. So this notebook will be shared with everyone so that you can actually try this out yourself. It can all run on a Colab notebook, so you don't need any special hardware for it. And so let's get started with this. Just maybe one prerequisite for this is that you will need to get yourself a Pinecone API key. And actually, I did it for the first time just this week, and actually found that it was incredibly easy to do. You can set up a free account, and you literally, once you have the account, you create an index, you have an API key, and that is all you need to connect to it. That was actually really, really nice. So you want to get that and save it somewhere. And then you also want to engage the GPU. The GPU actually accelerates anything that has to do with the transformers running. These transformer models are computationally very heavy, but because they do a lot of things in parallel, a GPU is actually very, very helpful in these situations. And luckily on Colab, you can engage a GPU. I'm actually just going to start installing this first because this takes a little while. But if you go into runtime, change runtime type, you can pick your hardware accelerator here. And you can get a GPU, which will definitely speed things up, often by a sort of magnitude of by about 10 times or something like that. So we're going to start off by installing the Haystack package. And here, we're actually going to install a specific version of Haystack, which contains the Pinecone document store. These changes and these contributions from the Pinecone team will actually be merged very soon in the coming days, actually, probably sometime early next week. So it'll be available on the master branch at that point. But for now, we're going to use this specific installation command to get just that branch and exactly what we need, just the components which are needed for Colab and Pinecone. So that's running through right now. I'm already going to start talking a bit about the next section, because this is where we start, this is where we connect with Pinecone. And we do that through a class known as the Pinecone document store. So here, what we need to provide is the environment in which the Pinecone index exists, and then also our Pinecone API key. I'm reading this in from a file in this case. And then we can initialize a Pinecone document store with these lines here. And I'm actually going to delete whatever documents are there, just to be safe. And then we're going to see how many documents we have. Okay, yes. This is actually one thing I saw a little bit before. This is something we can actually solve quite quickly. So in Pinecone, if you already have some documents in there, your document store doesn't want to overwrite it. So it's best to start off with a clean index. This is something that I'm just going to configure. Bear with me 1 minute. So yeah, I'm just going to delete the old index and create a new one. In the meantime, I can just give a little bit of a view of what's going to come up, because we're going to have some steps around data processing. We're going to prepare some data, including cleaning the documents and also splitting them. We're going to have a look at what it looks like once you've done all that. We're going to index these documents and also create embeddings. This is where you engage your dense passage retriever, this transformer-based model, and that's going to be computationally quite expensive, but it's sped up a lot with the GPU. We're going to have a look at what the vectors that we create look like, and then we're going to set up a QA pipeline around that so that we can start querying and getting answers to our questions, and also actually even playing around with the metadata filtering capabilities. So I'm going to look back over here. I'm going to recreate this index. So I'm going to call it document. We need 768 dimensions because that's what dense passage retrieval uses. Dense passage retrieval also expects the dot product similarity metric. And then that's all we need to create it. And it's initializing. And if we give that a moment, that should be ready to connect to Haystack. So I'm going to run this once more. See how that is. Maybe it takes another minute. Let's try that again. There we go. So we're now connected. What this printout down here is saying is that we have connected to the Pinecone document store, and we now see that there are 0 documents in there, which is just what we want, a fresh, empty index for us to work with. So let's now get to the data. What we're going to be working with here is a set of Wikipedia documents about Game of Thrones. Sorry, more specifically, it's the wiki documents about Game of Thrones. There are about, I think, 2,000-ish documents, maybe. Yeah, we're going to see that printed out in just a second. And then we've downloaded these as files. And what we're going to want to do is to convert them in something that Haystack recognizes as a dict. So there's a certain format that Haystack expects, and we have a utility function here that will already get it into that shape. So if we run this, it's gone through all these articles. And one thing to note is that the dense passage retriever actually has a maximum text length that it can handle. And so it actually makes sense for us to first chop up these articles into chunks of 150 words each, approximately. And yeah, that's what this node does. This block does. See that running there? And finally, we can have a look at what the output of this is. We're looking at one of these split documents. And here we have a Python dictionary with two fields. One of it is content and meta. And content is the string of the text that's in this file. And in the meta field, we find name, which is the name of the file, valamogulus.txt, and also the split ID. So once you perform splitting, one file might turn into multiple documents. Split ID just tells you which split passage chunk is this from this file. Now that we've done this, we can write this text into a document store. See that happening just now. And I want to stress that right now, by writing documents, we're actually just dealing with text. So we have, you saw that text, that dictionary up above where content was just text and there's some metadata fields. That's getting written into the document store. But what we really need to perform dense retrieval are vectors. What we want to do is to convert each one of these documents into a set of numbers that represents what it means, and to also index that into Pinecone. And that's what these steps here are for. So you can see that we initialize a dense passage retriever, and then we call document store.update embeddings using this retriever. What you see the program doing right now actually is downloading the models that are needed to initialize dense passage retriever. I think it's worth talking a little bit about some of the internals of dense passage retriever just a little bit, because it's actually made up of two separate transformer models. One is the query embedding model, and one is the passage embedding model. And the passage embedding model is what we're going to use to deal with the documents that we just pre-processed. And the query embedding model, obviously going to be used for the question of the query that's coming in. The thing to note about this is that the vectors that are created by these two models are going to be placed into the one vector space, so that if a query's vector is close to a document's vector, that means that this document is probably quite relevant to the query. And that's really what these operations of trying to figure out what's close to each other, as James mentioned, is something that Pinecone really excels at. So we have gotten to the point where we have downloaded our models, and there is some document processing going on now. And yeah, this takes a couple of minutes because this is quite an intensive task. As I said, we're putting all of our text through some transformer models. But yeah, the GPU that's provided by Colab it's really nice. They provided, actually, it's really awesome that that GPU acceleration is actually so readily available. But I also want to say that there are much, much bigger GPUs out there, and also that you can get GPU clusters, so that if indexing speed is something that's very, very important to you, there are definitely many levers by which you can speed up this process. So yeah, we're just going to give that a minute. In this step, as I said, it's creating the vectors and also simultaneously writing them to the Pinecone document store. That's all just happening in the background. You don't have to do any more to connect or to communicate with Pinecone. That's handled by this Pinecone document store. So while that's running, I'm just going to show a little bit of what we want to look at in the next cells. Once we have all this indexed, we're going to want to fetch one of these documents. So we're just going to get the first document from our document store. I'm going to get its ID, and then we want to look into this document specifically, return its embedding, and look at what this embedding is like. Yes, I think I just want to mention that this seems like a slightly roundabout way of doing it, but the reason is that embeddings, there are a lot of the embeddings that we have here are 768 dimensions, and if you have that at high precision for lots and lots of documents, that's actually moving quite a lot of information, and it can make it quite slow to fetch all your documents and return all their embeddings to get them to show in Python. This method that I'm using here just streamlines this a bit so that we're not actually doing this huge transfer of all the vectors because we don't need all of them right now. So yes, that's just going to need another couple of seconds. Yes. I want to stress also actually that with the dense passage retriever, as I mentioned, that there's actually the possibility to retrain it. So if you find the dense passage retriever is promising, but maybe not quite fully suited to the kind of language that you are working with maybe your very densely technical legal text or medical text or something like that, then you can create your own data set. You can retrain the model. And if you upload it to the Hugging Face Model Hub, all you'll have to do to start using it would be to actually change this line here. And actually, by changing this line here, you can use any other dense passage retriever model out there that has been trained. So for example, we trained one in German, and it's possible to use that just by providing the string there. Okay, that is finally run through. We've created 4,200 document vectors that have been stored in Pinecone. And let's have a look at one document and its embeddings. So yeah, here we see a vector is just a large collection of numbers, 768 of them, but we can see that this model has run and created some numerical representation of the meaning of this block of text. And now we can actually start setting up the QA pipeline. We've dealt with the retriever and the dense retrievers and the creation of the vectors. Let's now create the other components that go around it. So we're going to need to initialize a reader. And once again, here, to pick the model that you want, all you have to do is provide the string there, and you can automatically download something and start using it. And we're going to combine together the reader and the retriever in something known as the pipeline. This is how we glue components together. And we have this object pipe. And now we can already start querying. So to query, we call pipe.run. And we give in our query string. And also we can provide some parameters. So here we're providing the top K parameter to the retriever and the top K parameter to the reader. Top K in these cases just essentially means how many the retriever or reader should return to you. So by picking top K 10 for the retriever, that means you're asking the retriever to bring back 10 candidate documents that it'll pass on to the reader. One thing worth noting about this is that, oh, pipe's not done yet. Sorry, I have to run this cell. One thing that you should note about this, oh. Yeah, okay, that's going to take a second, is that the more documents that you pass from the retriever to the reader, the more work that this reader is going to do at query time. So this is actually your biggest lever for reducing query time. Yeah, the trade-off is that if you pass less documents to the reader, there's a chance that maybe you won't pass the right document to the reader. Maybe you'll have missed the one that you really need. So ultimately, this is a trade-off between how fast you want this model or how accurate you want this model. So there we have it. It's downloaded the reader model, and it's initialized the pipeline. And now we're performing querying on the pipeline. And yeah, there you see that it's run through, and we can see what it predicted. So let's now just print it out with the minimum amount of detail. And the question that we asked was, who created the Dothraki vocabulary? And the top answer that it returns is David J. Peterson. And to find out whether this really was the case, we can have a read of the context around it. So here you see the language was developed for the TV series by the linguist David J. Peterson. And this is the answer that we're looking for. One thing to also note here is that in the application we saw before, we found that different answers were assigned different confidence scores. If you want to see that, you'll want to print out your answers with more detail. And in this view, we still have the answers David J. Peterson, but you can see that it has very high score assigned to it, meaning that the model is very confident that this is a correct answer. And now, finally, I want to show the power of metadata filtering. and how it works here, how you implement it in Haystack. It's really, really useful as a tool in order to narrow the search space, because oftentimes you have metadata that tells you a certain article is just not going to be what you're after given a certain query. So in this case, we're going to ask the same question. And in the params, we're going to pass in a filter where we're saying that the metadata field name must be equal to 368 Jamie Lannister.txt. And if we run this and perform the prediction again, you'll see that the answers that we return are not the same, and they're all from this one document, which means that the filter is indeed activated. So yes, these are all the main components that you need in order to build a question answering system. I hope that you can see that it's not so daunting using Haystack. It only really requires this, I'd say maybe there are about 50 lines there or so. And we've tried to make it so that these nodes and these concepts that you're working with, something that are quite tangible and quite intuitive. We've really tried to document them in a way so that people can pick them up. But we're also always happy to help people out if you want to open a GitHub issue or chat to us on Slack and need a little bit of assistance getting to your QA system. But yes, this is all the Python code. These are the inner workings of a QA system. But it's also not an application by itself. Here we just have the code that could create a script that could let you play around and start asking some questions. But you might want to be creating something that really runs as a persistent application. Maybe you have a stream of requests coming in and that you need to handle them. Handle requests coming in from different applications. The script alone is not going to be enough for that. And so if you want to take that next step up, there is the REST API, which you can read more about with this link there. And you can really set it up in a way that you can communicate with it through HTTP requests. And also, as I mentioned earlier, you might have the desire to do some kind of domain adaptation to basically teach this model about the specific languages, the specific style of question answering that you're doing. And we have the tools here for it. There is an annotation tool that you can use to streamline the annotation process. And also we enable the ability to fine tune your reader or the dense passage retriever. There are tutorials for that. Have a read if you're interested. And yeah, all the best with creating your question answering system. That concludes my part. So I am going to hand it back over to Sophie.
Thank you so much, Brandon and James, for going through this notebook, the live app. Here are some resources if you all are interested in getting started with your own question answering apps and the Haystack Pinecone integration. We will be sharing, once again, this slide deck, which includes all of these links, the demo, notebook, tutorials, etc., and the recording in a follow-up email and by sometime tomorrow. If you put your question in the Q&A box, it should, almost all of them have been answered. There's one question for Haystack, Brandon, if you want to jump on that one. But if anyone would like to ask a question live, feel free to put more questions in the Q&A box. And Brandon, feel free to answer that question aloud as well.
Yeah, sure. I'm just trying to pull up this question. Give me one moment.
No problem. I can read it aloud as well. Does Haystack plan to add any HTML or beautiful soup style connectors, preprocessors for Q&A based on websites? And I can type the answer.
We actually have a web scraping component, so that it's a node that you basically just provide in the URLs that you want, and it will scrape those websites, turn them into text, and remove all the tags that you really don't need. If you did, I just want to stress here though that if you do want to have some sort of HTML or some sort of custom pre-processing or connector kind of component, we allow also for custom nodes to be created in Haystack. We have guides for that. So if you have a special kind of logic or you want to integrate like another package into your system, that's definitely very much doable with Haystack. It's not just operating as a closed ecosystem.
Okay, I think we'll go through a couple of the questions that we have answered as well. So I think the first one of those was, are there any limitations in terms of languages? If yes, what could be done to overcome that? So Brandon actually, I think, answered that pretty soon after you asked. But I just wrote that there are a lot of existing models currently out there. So I would definitely have a look at the Hugging Face Model Hub, have a look at DeepSet's models that they've been training. For example, they have the German Q&A model. And we also, over on Pinecone, we have some learning resources on, how these models are trained and which models you need. And I believe Haystack also provides data annotation and maybe also training utilities. I don't know if is there anything you want to add to that, Brandon?
Yeah, exactly. There are actually a lot of different things that you can do to adjust your language. There are lots and lots of models out there. As mentioned, we've trained a German DPR model, but also a German question answering model, a reader model. So if you are working with German, that's definitely very much possible. We actually have a page that talks a bit about, depending on your components, how to adjust to a certain language. But also worth mentioning, this is probably a little bit more sort of down the line, but there is work on multilingual models. There are multilingual language models. Language models are really like the base behind DPR and the base behind question answering. And with those, there's kind of this, there's a lot of research going into how can we train it just on a couple of languages in question answering? Can it then learn that for all the other languages? So it's really like a case of watch that space. I think multilingual NLP is on the near horizon.
Cool. Another question that we answered earlier is what limits the size of the database and latency between free and paid Pinecone accounts. So with free account, there's a limit of 1 million vectors, and typical latency for that would be lower than 100 milliseconds per query. There's a usage estimator on Pinecone, so it's like Pinecone.io/pricing. You can just type in like how many vectors you would expect to use and what sort of dimensionality, and it will give you an estimate for the latency and also pricing if you're looking at a standard account. The next question is from Ahmad. Does Pinecone support updating the index, or do you need a new index every time? And if indexing is needed every time, how fast is it indexing, let's say, for a couple million of documents? Greg answered this. I'll just reread what Greg said unless he wants to answer himself. In that case, please interrupt me. So Greg said, Pinecone supports live index updates. You do not need to create a new index every time. And we also have this new gRPC flavor of the Python client, which is incredibly fast. So you can upload data around 5,000 vectors per second. So for 1 million vector embeddings, it'll take you hopefully around a few minutes. And then the non-gRPC Python clients uploads at around 500 vectors per second. There are also other options. So if you have billions of vectors, we have other options for bulk uploading data. And you can contact Python support for that, Pinecone support for that. Another one for Pinecone's usage pricing calculation. Does an index need to be kept on all hours, or can you turn pods off over weekends or off business hours? So Greg answered this again. So within a month or so, we're going to introduce a feature to let you put an index on to sleep, so it doesn't occur any charges during that time. Another one from another question. Another one. So another open question is from Matthew. Is DPR better than sentence transformers for embeddings? I think that's think it depends on your use case and the sort of training data that you have in particular. So if you're using a pre-existing model, different models have been trained on different data sets, and if one of those data sets is more similar to your use case, then I think a sentence transform can outperform a DPR model, or a DPR model can outperform a sentence transform model. And if you are fine-tuning your own model, again, will depend on the sort of training data you have. I think Brandon probably has some good insight into this as well.
Yeah, I just want to add that sentence transformers is something that we actually have been using more and more. There are lots and lots of models being trained on that front. And if you look at the actual sentence transformers page, they talk about how different sentence transformer models are suited to certain sorts of tasks. So some are actually better if you're trying to find, if your input is a document and you want to find other documents that are similar, but it's a slightly different task if your input is like a question or a query and you want to find the document that's relevant. And there are models, you can actually pick models that are stronger at one or the other. And there are also models that are trained on both, so they have both capabilities. I can find the link to that comparison page and I can post it. And yeah, maybe we can send that link out in the email that's going to follow.
Yeah. Okay. Next question from Youssef. What are the specificities of each transformer used for the query in the passage? And also, what are the window slides for the transformer used in the passages? So for the, Brandon will probably add something to this as well. But for the retriever, as far as I know, we're in this example using DPR, which actually uses two-bit encoder models, one for building the query embeddings, another one for building the passage embeddings. Which are both training unison so that your query passage pairs are mapped to a similar vector space. So you encode your query and hopefully that maps to a relevant passage. And then on the window slide, I'm not sure what size is being used here. I was under the impression that the default is something like a small paragraph and there's some overlap between them, but Brandon, you can probably answer that.
The default length for a DPR what they call a context embedding is 256 tokens. That's sort of the maximum length it can handle. That is maybe somewhere around 200 words. So you could, yeah, I think if you chunked your passages into chunks of about 200 words, you should be fine. To be on the safe side, you might want to go down to 180 or something like that. Okay. But I just want to say that it's a very common technique to actually, if you have a really, really long document or lots of documents, it's a very common technique to cut that up into lots of smaller passages. You can also do it in a way so that your cut up passages actually have a bit of overlap so that you're not sort of like cutting an answer in half, let's say, or cutting a phrase in half. And that really kind of, yeah, you can get around this issue quite easily like that.
Cool. So just, we're kind of over time. So just to, we have one more unanswered question in the box, which is, why is the length of 150 considered? Is it due to the max token length for typical transform models? So I'm not sure where that 150 is coming from, Brandon. Is that?
That's basically the same here. I just picked a very conservative number. Yeah. So once again, yeah, the max sequence length is 256 tokens. I picked 150 just to be extra careful there.
Cool, perfect. Yeah, so I think we can sort of wrap that up. If you want to finish with anything, Sophie.
Yeah, thank you both so much for answering those questions. If you have other questions, please feel free to reach out to us or to Haystack. The links to Haystack's Slack channel as well as our community page will be within the email follow-up, which will also include the slide deck, recording, and all the demos and things that you saw here today. Thank you so much for being here. And again, thank you to James and Brandon for hosting this with me.
Thanks for everyone who came along today.
Thank you very much. Thanks, everyone. Bye.
Bye.
Bye.